Hey everybody. Thank you so much for having me. I'm very excited to be here. I love anti-forensic stuff. I love to do research and mess around, and that's basically what this talk is. So the talk, as you can see, is anti-forensics AF, and when I would see that meme like on the internet, like that's stupid AF or that's silly AF, I would always read it as that's stupid anti-forensics, and I thought it was something different. So I'm the rapper in dual core, as Mark said. If you guys have played Watch Dogs 2, our song All the Things is in Watch Dogs 2. You can pirate it on BitTorrent or wherever you get music from. I work on a red team, so I hack computers, I write malware, I get shells. I love to mess around with stuff and just have a good time in general. So we're going to talk about anti-forensics today, and I'm going to pick up kind of where I left off on my last anti-forensics talk, which was doing some stuff to tamper with like memory forensics. All of this is coming from the viewpoint of an operator, where like you are somebody that owns a system, you have a shell, you have access, you drop an implant, and you want to maintain access onto that system without getting detected. And if you do get detected, you want to inhibit the forensic investigation process so that the blue team can't derive like good IOCs to find you elsewhere in the environment. Right? We all spend a lot of time like crafting our own tool chains, writing our own malware. It's a pain in the butt when it's all burned, and then you have to like write a whole new tool chain. We'll cover doing this with like Windows and Linux stuff, so you'll see that if we tamper our executable in memory, we can like cause a lot of problems for forensics tools and win as red team. This is good. Previous versions of this talk have some Android stuff in them, and I'll kind of touch on it, but I actually added a little different stuff in this talk just for you guys. So we'll cut the cameras at that point, and I'll like kind of go off the record a little bit. And then I'll show you some fun stuff we can do with SD cards, and we'll play like a little mini CTF all together. It'll be really cool. I don't know why that didn't play. Okay. So all these disclaimers out of the way. I don't do forensics professionally. Like I said, I work on a red team, so all of this is just me messing around with stuff. I love to mess with everybody. So like I love to give our blue team a hard time. I love to give like our enterprise security folks a hard time. Everybody. I'm not an expert at all. I literally just like sit at my desk and like roll my head around on the keyboard after I drink like a dozen vodka Red Bulls and just see what happens. And I'm pretty sure everything that I've learned to do, that I've taught myself, is like illegal, or I've done it by violating some law. So do illegal things and like learn cool stuff. That's kind of what was supposed to happen on the okay, so let's talk about memory forensics. Right, from the standpoint of an attacker, we're thinking about malware in terms of software protection. Right, like we spent all this time writing malware. We have this cool implant. We get like cool shells. We have good functionality, like TTY implementation, whatever. And we don't want blue team to find that, reverse it, and then like find our C2 infrastructure and burn us. So if we're on a box and we see like somebody sniffing around, we want to like persist in like thwart detection. And if blue team is on our trail, like it could be like they're investigating like a weird log entry or whatever. For any reason, they're like closing in on our malware. We want to prevent them from either acquiring or analyzing the malware that we've spent the time to write. So, I'm thinking about this, I'm like, what are all these ways I can do this? In previous talks, like I've actually like Trojaned like the actual memory forensics tools when they like get on the system, which works really well. Like I had whatever Mandiant's tool was at the time, I like Trojaned that and had it write out in memory like troll instead of like actual memory context. So this is cool, right? Like memory stuff is like the new hotness, like old dead disk forensics is like old and busted. So you have all this stuff going on in memory, and what happens is like your program first is on disk just as a file, right? And you have all these sections. The sections contain like code or data or resources or whatever. And then when you load from disk, that's when you're in memory and you start to have fun. So with all these sections, once you're in memory and your code is executing and you're running, if you don't need a section anymore, there's no reason for that section to be in memory. Or there's no reason for its data to maintain its integrity. Meaning, we can either remove it, overwrite it with zeros, or overwrite it with like something completely different. So when we do stuff like that, we tamper sections that we no longer need in memory, the analysis tools, they still need that data, right? So they have a really hard time piecing together what actually happened if you give them bad data. So as the attacker, lots of fun to be had. It's great. Okay, so this is my first demo. It's this program that I wrote, it's POC, called The Keys Are Like Right Next to Each Other. And then in this demo, we're going to use Recall, which is an open source memory forensics analysis toolkit, and we'll use WinPmem to acquire memory. So let's do it and see how it goes. Okay. One sec, I'm just going to mirror the displays, and I think it'll make it easier on all of us. Nice. All right. Now, if I can... Oh, of course, I went to sleep. Super helpful. Oh, I forgot to mention in my bio slide, I also am a big fan of Mulan, Szechuan, teriyaki dipping sauce.
9 more seasons?
Yeah, 9 more seasons, 97 more years.
97 more years.
All right, cool. So here's just like a Windows VM, right? Windows target, whatever. Let's start our malware. Let's let the VM catch up, I guess. Jesus. Oh my god, this is terrible. I'm so sorry. I feel like I'm on a 56K modem or something. I'm gonna like reboot this VM because I'm like hating my life right now. I apologize. I'll tell you guys a really cool thing I learned recently. So like my friends like to debate the stupid naming of GIF versus GIF, right? And so they're like, you know, I have this one contingent of friends that is adamant that it's like it's GIF, G-I-F, like G, and then the rest of my friends are like it's definitely GIF, like a hard G. And I did some research into it because I'm tired of like this stupid flame war on IRC. And what I found out was it's pronounced like the G in gigantic. This is making my life worse. I hate this. All right, here we go. Should have done like a snapshot or something. All right. You might have noticed my password is extremely short. It's 1234, same combination as my luggage. Just in case not all of you have the 3D printed TSA keys. Tony Award for slowest VM ever goes to me. All right. Yay. All right. Cool. Our malware is running. Here we go. And I don't think this one prints anything. I just think it just runs. So. This does not get keyboard input. Okay, cool. Can you guys see that okay? Is that big enough? All right, cool. All right, so malware's running. Neat. Windows not refreshing. Fine. So let's acquire memory. So to do that, we're going to use WinPmem, and we're just going to write it to an output file. We'll just call it LOL. The AFF4 is like its own thing. So here we go. We're going to acquire memory. I guess while it does that, let's like do something else because that might take a minute. Let's watch a video.
No more goats.
Hey, this is my presentation. This is called Guy on a Buffalo.
One day the guy on the buffalo hot dog stretched his legs.
video's amazing. I've played a couple shows with these guys, the Possum Posse, and they're fantastic. That was episode 2 of 4. I highly recommend. All right, and our memory acquisition finished. Great. All right, so let's load up recall, and we'll take a look at what we got. And remember, our malware is still running. So we should be able to get the malware out right. That's our goal, is trying to get the malware out. Alright, so I have to write all this down, so my brain's all over the place, as you can tell. Okay, cool, so we load recall. Recall basically gives you this like IPython interface, which is really nice. You get cat completion. I think it's got like, Python stuff in it as well. So we do PS list, we get a listing of like processes that we see from the memory dump, right? This is us looking at this like lol.aff4 file and seeing like what's going on. So there's our like conmu stuff, there's Google Update running in the background. The keys are like right next to each other, so the malware's still running. Cool, let's try to grab it. So we use this module called procdump, and you can actually just specify a regex. Like if you guys have used volatility before, you have to find the PID first, like the process ID, and tell it, like dump this PID. But in this case with volatility or with recall, we just say like, oh, the process that I want, it's got like this in the name, and it's like no problem, here you go. So then let's dump it out to the desktop. Alright, cool. Now, while it's doing that, I'll just show you guys real quick, like in hex editor and like IDA, like what this program looks like normally. So here's the original. The keys are like right next to each other. This, standard stuff, right? You see like got our MS-DOS stub up front. Here's our PE header, sections. Like we're good. Everything looks totally legit. Let's toss it in IDA, and we should see like a nice call graph. Again, this is the original binary, right? That's like currently running. So yeah, easy peasy call graph, all the like subroutines defined. Like this is normal, right? If you're doing malware analysis, this is what you want to see. So let's close out of that. And okay, there's our output executable dot. So here it is. So let's take a look at this in the hex editor. Oh man, it's all zeros. Okay, let's put it in IDA. I think there's like more garbage like further down, but it definitely doesn't look like the other one. IDA thinks it's now a MS-DOS com file, so let's see what it does. Oh no, that doesn't work either. Huh. But our malware is still running, so we win. Attackers win. Red team wins. That's awesome. All right. Eat it, blue team.
Did you hook just did you hook IDA and HXD, or did you actually hook recall?
Actually, what I did is instead of tampering the forensics tools, I had the binary rewrite itself. So I'll show you the source code.
Okay.
Let's see. Okay. So if I bring this over here, can you guys see? Can you see that? Okay, is that big enough? All right. So what we're doing here is this is the source code for the POC. First off, we just find the MS-DOS header in memory with the 45A magic bytes. Then we find the PE header, come down, get the size of the header so that we know like how much data we need to overwrite. We call virtual protect, which changes the permissions of the page in memory so that we have a write to it. So now we can like write data into it. When it's originally mapped, it's like read and execute. So if we try to write into it, we'll get like an access violation. After we have changed the permissions, we use RTL0 memory, which is essentially just like a wrapper for memset, to just write zeros into that section of memory. And then we'll restore the initial protections with virtual protect. And then at the bottom here, I'm just like looping infinitely so the malware just keeps running. And so that's it. Like it just rewrites zeros for the header, and it's awesome because it beats the forensics tools. You can do like other things if you like get interested. You can write like random or like interesting values into like certain fields in the header, and when analysis tools like IDA or like I'm not sure which other tools, but some other tools when they go to parse those values, you get like weird behaviors because they're expecting like a large number of bytes that they need to like read or write, and there's like or a small number of bytes and then they read a large number or something like that. So you can get some interesting behavior. So that was, the keys are like right next to each other for Windows. Okay, so this is kind of recapping what we did, right? We don't need the PE header after we've loaded, so we can just do whatever we want with it. In this case, we zeroed it out. The process is still running, so our malware is still active. We still get our shells, like keep kicking butt, but the analysis tools failed. And so where I left off in my previous talk was like doing this on Windows XP, which was before it was end of life. And as you saw, like it works in Windows 10, so it's still a valid attack. For completeness, if you guys like, I mean, I guess it'll be up on YouTube or whatever. So if you're playing along at home and you want to just like pause the video and on the slide, there it is. That's what I typed. Okay, let's try it for Linux, and then instead of using recall and WinPMap, we'll do line and volatility. So, and unfortunately, line is like a lot faster, so there won't be time for a guy on a buffalo. All right. So, can you guys see that okay? Yeah. All right. Cool. So let's actually, I guess. Well, yeah, I guess we can do it. All right. So malware's running. Right, you'll see it pop up down here. Elf header size. This is like debugging output, doing evil stuff. You'll see it just keep doing evil stuff. So one of the things that's interesting with volatility, and Lime specifically, is like, or with volatility specifically, is it doesn't ship with a profile for doing memory forensics on Linux systems. So you have to build the profile yourself. So I'm just going to kind of like run you guys real quick through building Lime and building the volatility profile, and then that way, like if you want to do this at home, hopefully it'll be easier. All right, so here's Lime. You just get it from GitHub. It's like a Git clone, nice and easy. So let's see. I think I have a copy, so I'll just like make clean it. I think, let me just, all right, cool. Cool. Okay, so all you need is, oh shit, I shouldn't have done that. I think it's just make. Yeah, okay, cool. So a simple make will make the files for you. Then you insmod it, so you're inserting a Linux kernel module. And to like match your kernel version, I just kind of like do this shorthand like every single time, so I can just copy and paste it with the uname-r stuff. And you can see, I mean, this is like that's the module that got built, right? And cat equals, and then this is where we're going to write our memory output to. So we'll call it lol.lime in temp, and we'll tell it the format is line, which volatility can parse. So inserting the kernel module will start the memory acquisition for us. Meanwhile, we're still running, right? We're doing evil stuff. Still good. Cool. All right, so now memory acquisition's done. Should have a file, lol.lime. Nice. All right, cool. Let's do some volatility. This is where it gets a little tricky. So I'll start you guys off, and we'll make the profile for Ubuntu. Okay, so you go into subdirectory called tools, and then Linux is underneath your volatility checkout, and you do a make. I think I'm going to make clean first just in case. All right, and it should produce this module.dwarf file. And you should head in, you should see this like .debug string. So there it is, .debug info, and that lets you know like the file built okay, everything's legit. All right, now you need to create a zip file in a certain directory. So you put in this volatility plugins, overlays, Linux, and then I'm just going to call it Ubuntu 1604.zip. And then we give it our new files that we just made. Tools, Linux, modules.dwarf, and we give it the system map for the current running kernel. Again, using that uname-r shorthand to get the current version. So we do that, looks like it created everything, cool. All right, so now we can get our profile name. Let's see. So here's our vol.py. And if we do --info, we can grep for Linux, and it'll show us any profiles that we have that start with the name Linux. All right, cool. So this is the one that I just built, right, the 16.04. So let's use that to process our memory dump that we grabbed with line that's in that temp directory. So vol.py -f, our file, this is like our memory acquisition file, lol.line. The profile is this Linux one that we just built. And let's do a PS list so we can get the process listing, and that'll give us the process ID of the malware, and then we'll try to dump it out. Or we'll extract it from the memory dump. Alright, so there's our process listing of everything that was running when the acquisition was taken. Here's the keys are like right next to each other. 2383. You guys can see that in the back. Cool. So let's do Linux proc dump. We'll put it into temp, and we'll give it was 2383, I think, right?
Yep.
All right, so here we go. Fingers crossed. All right, cool. Looks like the warnings are just like missing these storm modules that are missing, which that's fine. It's not an issue. But no complaints about like dumping the executable. So we're good. All right, I think. All right, let's take a look at it. Let's run stat. What was it called? The keys. Okay, there's definitely a file there. But one thing that looks weird to me is that the file size is 0. So let's like hex dump it, see what we get. Oh no, it's empty. But our malware is still running. So good job, attackers win again. All right. All right, cool. So let's talk about what happened there. And I'll show you guys the code as well. So this is like almost the same thing as the Windows version, except I kind of do some like lazy programming here, right? So to find myself in memory, I read into proc/proc, which has like all kinds of stuff about what's going on in the process. It's not a reliable way to do this. I've been on systems where like you don't have access to proc, where like it's just like they've totally restricted it. So this is bad, and I should feel bad. But it works in this case, and so like I don't give a fuck. So I find my start and end address for the header in memory. I've got debugging output, which you guys saw when the malware started running. And then here, instead of virtual protect, we're calling mprotect, which is essentially the same thing. We're just changing page permissions, adding a write, so now we can write into the page, and then we're calling memset, writing zeros into the header that's in memory, and then restoring the original permissions with mprotect again. And then we just loop. Yes?
So let's say like in a red team engagement, you have another red teamer that like has another rootkit that messes with proc, so they like throw a wrench in this whole red team tool then?
It would with this part up front with getting the base from, the question is, if there was another rootkit that messed with proc on a system, or like you're restricted from proc or something like that, would it mess with this particular tooling? And it would in this case because of the lazy way that I did finding myself in memory. You can totally do it like in a normal way, but I was just lazy, so. in this case, yes, I would mess with it, but if I did it right, I could get around it. All right, so that's that. Let's.
Why was the file size 0 instead of it just being a big file full of zeros?
Why is the file size 0 instead of a file being full of zeros? And I'm not actually sure. My guess is that because I haven't debugged it to like give you a 100% definitive answer, but my suspicion is that when it tries to read into the process structure, like in the header, it reads like a size of like the file or something like that, and it just sees 0. So it's like, oh, it's 0, and then it doesn't even try to like read anymore. So you could technically you could DD from the memory image and then just be like, okay, like I have this blank header, but I have like a bunch of code here, and you can put it in IDA and like start hitting C to like get it to represent code. But like you might not be hitting C in the right place, or you might have like anti-disassembly stuff in there as well, or like all kinds of other things could go wrong. And from my perspective, my experience, I only know like one forensic analyst that has the know-how to do that. Everybody else that I met that does forensics, they'd be like, oh, it's just an empty file. I'm like, oh well.
Were those zeros or nulls?
I mean, it's 0 and binary, so it's not. Yes. Oh.
So one of the things that we're doing is pulling the image out of memory and trying to read it as a file. What if we just like attached GED to the image and like jumped right into that port and kind of got our data from there?
Sure. Yeah, you could totally try to attach GDB to it. In which case, like the counter for that from like the red team side would be to like mess with ptrace stuff, right, and like prevent do like anti-attach stuff and like anti-debugging stuff. Yes.
If people see like your red team, blue team see things like a bunch of 0-page memory things, you're going to know that somebody's been doing something with it. Well, instead, why not just like copy, pages from a random process into it, so that at least it looks like it gives you some semblance of maybe you hope that they don't even notice that there's anything weird about it.
Yep, and that's a great point. The point is like why write zeros, which is like an anomaly when you could like write something that looks normal. And like another thing you could do is like I don't know if you've seen like tiny elf or tiny PE, which are like they're like minuscule like executables. And what you could do is like write that into your header, right? And then like if somebody dumps that out, they're just like, oh, it's just tiny PE, which is still like weird. Like why would tiny PE or tiny elf be running on a system? But like you're right, it's not just like a complete red flag of like all zeros. So yeah, it's a good point. Yes?
So how would this system cope with a write XOR execute policy?
It's fine. Like if you've got like packs on the box or whatever, like your OpenBSD. The question is like, how does the system cope with the write XOR execute page permission setup? And it's the same. Like that's the reason we're calling like mprotect, or we're calling virtual protect. And that's to modify the page permissions, right? So when the executable maps into memory, by default, that page permission for the header is only read and execute, so it's execute and not write. And so we're making that extra protect call or protect call to like add write permissions, and then we write, and then we remove the write permission to restore the original. All right, let's. Oh yeah.
So, philosophically, what are you protecting yourself against? Because the forensics blue team already know your process ID. They know which process you are running in memory. They can kill it at will. What are you protecting?
I'm protecting the time that I've spent like developing my malware, my implant, my framework, like my whole tool chain, right? Once that's burned, then we have to like build a whole new tool chain.
Is it no longer on the disk?
Yeah, right. And so like in this case, it's POC that would stay on the disk, but like our stuff will like remove itself from disk. Nice. Yeah, writing malware is fun, but also like time intensive. All right. Okay, so like the Windows one, right? We don't need the elf header either after loading. In this case, we're not doing any like multi-stage unpacking or any stuff like that. So we can zero the header out, memset, or write random values to it or whatever, and our process continues to run. So like we're still operating successfully, but the analysis tools fail. So that's pretty rad. For completeness, this is like the entire process: doing git clone, building the kernel module, installing it, or inserting it, building the volatility profile. Yeah, just doing volatility stuff with my volatility friends. Okay, Android stuff, so I'm just going to like briefly touch on it. Basically just like use encryption, and that's it. The Android tool that I have, all it does is turn your phone off under certain circumstances. I always like this, use Tor, use Signal. So I'm planning a Thanksgiving dinner, use Tor, use Signal. My wife left me and took my dog, use Tor, use Signal. I'm preparing a meal, the recipe calls for milk. Can I substitute almond milk? Use Tor, use Signal. I want to eat a pint of Cherry Garcia ice cream. Should I use a bowler or not? Use Tor, use Signal. Selling social security numbers for Bitcoin. Please contact me on Jabber. Use Tor, use Signal. So my app was called Duck the Police, and I just started that you had root on your device and encrypted, and you just use the sensors. I wanted to use magnets as well, but I don't know how they work. And then that was the only picture I could find that said Duck the Police, so these are the next closest ones. That one I love. I have a friend that picks locks, and he's like, the police charge you $125 to remove a boot from your tire. I charge $75. The bubble page. OCR difficulty God mode. Okay, can we cut the videos? Okay, so I have this SD card. Regular SD card. The physical lock is not set. If we were ideally able to play this game, I would hand each of you a copy of this SD card, and we'd all play together individually. But there's one of me, and there's like way more of you, so you just kind of have to like play along with me as a crowd. All right, so we put the SD card in. We see there's a file. Cool. The rules of the CTF challenge are easy. Add your name to the end of the file. Once you've done that, ensure the file is saved, sync it, and we'll survive being ejected and remounted. Success must be validated. Enter your name below. All right, pretty easy, right? File's already mounted. Let's just edit it. Add our name. There it is. Great, cool. Let's unmount it. Cool. Take it out. Put it back in. Here's the text. Oh no, our name's not there. But we didn't get any errors. Thoughts?
Hold it before it could write to the disk.
Good thought, but you mounted it, so umount does the sync, so all the buffers have been flushed, everything's been saved to disk.
It doesn't necessarily flush it right away.
It won't eject it until it's synced. I can do a sync also, but it's taken care of. But good thought. Yes.
TempFS file system.
I'm sorry?
TempFS file system.
Okay, good thought. It's not TempFS, but good thought. If you've already seen this, by the way, you're not allowed to play. Just FYI. Yes.
You have an entry in your FS tab.
Entry in the FS tab. Nope, FS tab is completely normal. But that's good. We could check like mount flags, right? If it was mounted like read only, when we would have gone to save out of bin, it would have complained that you're trying to.
Yeah, I don't know. I don't remember all the options.
Sure, but good thought.
You like switch to a different user or shell, look for like LD preload floating around in your home directory and make a bash profile or something?
Yeah, good thoughts. So like environment variables and stuff like that, doing like an LD preload, like loading a library, messing with like mount or something like that. All the user tools are all the same. Like ideally, you guys would all have a copy of this and be doing this as well. So there's nothing, I haven't touched any, like my operating environment doesn't have anything special going on.
The file is crafted in some way. It's not like a normal text file.
Good thought. Regular text file, we can like hex dump it and take a look at it. That's the whole content. So there's all the bytes. Good dot. Yeah, in the back.
Is the physical media somehow preventing the write?
No, but that's a good dot. So the lock switch, like for example, it's set to the unlocked position. If it were set to the locked position, we would have gotten like an error saying like, you know, this is like in read-only state. Good dot.
Do you have something that automatically runs when you mount or unmount the device?
Good dot. Do I have something that automatically runs when mounting or unmounting? Nope. Like that's everything is like the operating environment's like normal. Like it would be like your own operating environment as well. Like if I gave this SD card to you, yeah, John.
You're willing to DD the SD card a bit of it and run Finwalk on that?
Yeah, we could totally DD the card. It would take a bit because it's like a like we can DD it, but I'll tell you, like even if we DD back onto it, it's still going to be the same image at the end.
Yeah, but we'll just want to look if there's any other weird stuff.
Yeah, we can. How about like if we run strings against it?
Yes,
I saw another hand in the back. Yeah.
Turn it off and on again.
Turn it off. I like that. Nice. I don't know why strings isn't finding anything. Oh, maybe because it's mounted? I don't know. But yeah, we could literally, like, we could try, like, DDing the entire card, like, manipulate, like, the disk image, like, right back onto it. It's a normal, like, extended 4 file system. Yes?
Is the SD card's firmware? Like,
Yes. Yep. So what we're doing is we're tampering the SD card firmware from userland. So nice work. Here, have some Swedish fish from Fish Week. Oh, sorry. That's why I computer instead of sports. All right. So there's this tool that I use called SD Tool, open source. And if we run status, we see that write protection state is temporarily enabled. So we can unlock it. Now the write protection is off. Take it out, put it in. Unmounted, pull it out, put it back in. And we did it. So you might be like, BFD, IDJF, or GAF, like, what does this matter? Why is this important? Who cares? And I think it's kind of cool for a couple different reasons. Whoa! It's not even a goat. So the reason this is cool is because you're operating totally normally, your OS is not complaining about anything, but you're not logging anything either. So you're not creating any forensics evidence, which is pretty rad. So a couple of caveats. A lot of USB hubs, they show up as like a different device. So you won't be able to necessarily use a USB hub in this case. You might need like a direct MMC writer, which is why I have 2 laptops, because the SD card on this one doesn't work. But the things that I like about this, right? Like we've done some like Android implant work. Like we made these Android devices. We have like Radius at work for Wi-Fi authentication, which ties into like AD. So we like put these Android devices in like the bathroom. People sit down and go to the bathroom, and then they like auth to the Wi-Fi, but it's actually our Wi-Fi on our Android device, and then like we get their creds, right? But if the Android device gets collected by the blue team, then like I don't want them to get any evidence. Or if it gets collected by some rando, like I don't want them to get anything off the phone, right? So if all your evidence is going on like a micro SD card that like can't save anything, and you tie that in with like the anti-forensic stuff that turns the phone off and the phone's encrypted, everything's protected. So it's good. If you run your attack platform off of SD card, right, you can totally operate all the time, do illegal things, and then there's like no evidence and no crime, so it's good. Portable Pi from the Gruff, like I've modified his install a little bit for a few more things, but it's basically like you take like a Raspberry Pi and it just like routes all your traffic through Tor, and then you don't have like any leaks of like DNS stuff or WebRTC stuff or any stuff like that, like bypassing your Tor stuff. Literally everything is run through Tor. So put that on an SD card where you've got like the right protection term, you're good. So
Could that portable Pi be, because I realize, I tried to do this myself, there's no version of Tails for Pi. Could this be a substitute?
yeah, you can do that. So you won't have, Tails is like having multiple VMs, right, with the middle box, and this is basically a physical implementation of the middle box for you.
I still don't know what this is.
Anyways, so this is SD tool if you want to grab it. That was ladder code. If you guys haven't seen that video, it's just like a 9-minute video of this guy laughing in this hysterical manner. This is how you use it. I used Clang to build it instead of GCC. GCC didn't want to work for me, but Clang did, so that's fine. And